Now we know at least the basics of the classical transport layer protocols UDP and TCP. Let's have a look into some newer developments. I will pick out 3 examples, as you will see: multipath TCP, QUIC, and STP, touching some other protocols. So let's have a look back. So what happened in the previous chapters? We saw that a client sends a packet with a header and a payload across several domains, routers, etc. to a server. And we always said, okay, if we have this end-to-end communication, and that's the idea for the transport layer, we assume relatively smarter, intelligent, whatever this means, end devices and a relatively dumb network. The main purpose of the network is to forward our traffic. And it's up to the transport layer now to add some additional services, not only the multiplexing based on the port numbers, but, and that's quite important, flow control to prevent flooding of the receiver, congestion control to prevent flooding of the network, and very important, reliability. We learned about the windows and acknowledgements and checksums, etc. And this was all end to end. So end to end, that was the idea, across the network. So the end systems determine what's happening in the transport layer. We know TCP is the dominant protocol for the transport layer. We know how it works. The 3-way handshake, yeah, it's a bit more complicated compared to UDP. It offers this 3-way handshake. Then we transmit something. We know about the sequence numbers. We can transmit. We get the acknowledgement. And we tear down the connection. So that was the basic idea. But this also shows you, well, okay, this is one round trip time. This takes some time. We can combine sending acknowledgement and sending data. That's fine. To tear down, that's again, you see the round trip times involved here. Okay, this costs some time. So I will come back to this, how we can maybe improve this. So what is this section about? This section is about recent transport protocols, so a bit newer. So, and we will see what are the challenges if you want to really design a new transport protocol. And not only the design, but also, and this is really a big issue, successful deployment. We'll see that there are dozens of transport layer protocols never really deployed or deployed only for special purposes. And in the end, we have some lessons learned from multipath TCP, QUIC, and STP. So, what have we seen over the last more than 40 years? So TCP, the first ideas already started in 1974, but the standards are from the early 80s. And during the following 20 years, there was a lot of research about optimizing TCP, not about implementing something completely new, a clean slate approach, so now let's start something completely different. No, it was about optimizing. But after 20 years, many saw that, okay, we have some fundamental issues with TCP. TCP is fine for many, many purposes, but there are some issues, like, for example, the head-of-line blocking. Remember the issue for delivering, for example, different parts of a web page. So we'll see that one of the ideas in 2000 was STP, a protocol that really never made it into all the end systems, but is a part of the standard for mobile communication systems. There are some more developments. We never saw them really deployed in larger scales. And we will have a look into multipath TCP and into QUIC. But why is it so difficult to come up with a new protocol? Well, we will see one of the major reasons is that TCP is so dominant. And this has certain consequences. So why having different transport layer protocols? Well, quite simple, because we have different applications. TCP is perfect for streaming, let's say, larger amounts of data. TCP has fairness, and TCP is quite efficient when it comes to large amount of data. But TCP is not good, for example, if we talk about this head-of-line blocking, and this is where we have this SCTP. I will come back to this. This can be used for signaling in telecommunication networks. TCP can also not handle different paths for the data simultaneously. This is where I will come back to multipath TCP. Then there are some other developments like, well, can we make, for example, UDP in a more reliable way? Or can we make it even lighter than UDP? Yes, maybe only partial checksumming, things like this. Or can we make a UDP more TCP friendly, etc., for different purposes? Or can we have a special protocol more geared towards what the web wants? I will come back to quick. So, yes, there are certain requests for new transport protocols. And many of these new protocols are driven by, we want to have more reliability but reduced latency. Plus, there's a new aspect of privacy. And we know that when it comes to latency, we always have these round-trip times, and we know the three-way handshake, and it takes some time and privacy. Yeah, we have to add on something on top of TCP, so transport layer security. Maybe we can integrate this, make it faster and secure, but still reliable. Okay, so let's start with a new transport layer protocol. Wait. So if we look into the transport layer, for example, at checking at one of the larger IXPs, so where a lot of data comes together and is exchanged, remember, this was this peering between different providers, then it can be seen that this was a measurement some years ago, that at least TCP is quite dominant. So more than 80-90% of the traffic is still TCP. Although I told you in the context of the web, Quick is coming, but still there's TCP, a lot of TCP traffic. Why is this the case? Many efforts to change this, many efforts to implement new protocols, but there's a problem. And this problem is well known, and it's called the ossification of the transport layer. What does it mean? Ossification. So the transport layer, the use of TCP and UDP, is more or less some kind of hardwired into the network. Why hardwired into the network? Well, they are the APIs. So APIs, that means your operating system has to support the new protocols. And if the big vendors of operating systems don't want to support the protocol, then tough luck. Yes, there are free operating systems, Linux, etc. Then you have some experimental implementations, but if still the majority doesn't support it, if the big servers don't support it, you cannot simply roll out a new transport layer protocol. So that's a problem. So you need the support of the APIs. And the APIs, the classical APIs, they support UDP and they support TCP. Okay. And if there's no more support, well, you can only use UDP and TCP. What else? Now we'll have a closer look into this. They are the so-called middleboxes. We touched this already in the context of NAT, network address translators. So those middleboxes, they also assume something about the transport layer. Remember, for example, they do network address and port translation. So they assume there is a certain address and also a port at a certain location in the packet, because they know, okay, for UDP it looks like this and for TCP it looks like that. So they also support TCP and UDP. And what happens if your NAT box does not support your new fancy transport layer protocol? It will simply drop the packets. It cannot process it. Then there are also some commercial interests. Why not implementing this and that? So there are many different interests. So there are certain challenges when you want to deploy a new protocol. And this altogether led to this, what it's called the ossification of the transport layer. So the transport layer is not flexible anymore. So again, let's have a closer look into this. I told you we started, transport layer, this is all end to end. So that was the idea. told you, end to end. That's our transport layer. We transport, and we basically have this virtual pipe here in between. Okay, and in between, we have a network that simply forwards the packets. So this is where we have many of our routers all over the place, and our protocols, etc. But overall, the network itself is rather dumb. Forwarding the packets. Okay, so but is this still valid? That's what you will find in the textbooks, and that's what I also taught you. But I will also tell you, in reality, the picture is a bit different. And this shows you that in reality, on the way from one end system, so we have a host here and a host there, we not only have our routers with the single purpose to forward our packet, that's one thing, but we also have what we call middle boxes. So boxes in many different places, like, for example, firewalls. So firewalls looking into something on layer 3, but also on the application layers. Okay, we have proxies, different gateways. We have load balancers, VPN system for private networks. We have net boxes, and so on and so on. What does this mean? So we have on the path from an end system to another end system. Our path does not only go through many routers, but also through many middle boxes. And the problem, I will show you in a second what the real problem is. So those middle boxes, like NAT, they can not only look into certain protocol header fields, they can also, and they will, manipulate them. But that also requires that the middle boxes understand the transport layer protocol. They break the end-to-end paradigm, yes, but that's the way it is. So we have many different types of middle boxes looking into everything, like different gateways or load balancers. They say, for example, okay, if I receive, let's assume we have a load balancer here and you have a large network of many servers here, and you have an incoming request, well, using a TCP connection, then the load balancer says, okay, this request for a certain web page, I will forward to this server, and further on, all the requests for this from a certain end system, I will forward to this web server. Then the web server has the state and can handle everything, etc. But this means that the load balancer has to know layer 4. Because then the load balancer sees, this is a TCP SYN, this is a SYN ACK, this is whatever, setting up a connection, this is a packet that belongs to a certain connection. And if the load balancer only knows TCP, what can you do with another protocol? Nothing. Load balancer doesn't know how to handle it. So, what is the problem? So we have these middle boxes in between, and not only the routers. The problem is the middle box can be active on almost every layer. On every layer. So, because it's a packet, and you can look into the packet, not only for spying, eavesdropping and all these things, but just for manipulating it for good or bad purposes. So, more specific, what do we do? Well, typically in a router, this is what we all know. This is our IP packet followed by a content, TCP. So we see the IP header, the TCP header, and then the payload. So the router may look into TTL. So if TTL is 0, we know we dropped the packet. The router with version 4 maybe has to fragment the IP packet. Okay, and if we do so, the checksum changes. So the router will typically change then depending on the TTL, the checksum, and maybe deals a bit with the fragmentation if required. But at least TTL and checksum is changed. But that's it. Okay, that's the classical traditional way, and we do not touch payload and all the other things. Now, what is the situation in reality? We have the middle boxes. So the middle boxes are at home the network address translators. So you have your, as you learned, the private IP addresses typically here, and then you translate this into a global IP address. Okay, Then we have many other systems in between, like load balancer, firewalls, etc., etc. And what they do is they break the end-to-end communication. I told you this before in the context of NAT, that NAT breaks the end-to-end paradigm. So, what is, for example, processed in a NAT box? On the left-hand side, you see IP packet, classical TCP packet. So, and NAT now plays with, as we learned, the addresses. Source address, destination address, but also the ports. This is our network address and port translator, and the checksum, and the TTL, etc. So, but checksum, TTL, that's what also the normal router plays with. But now, additionally, we see a normal NAT box also changes the addresses. And now, I mean, a middle box, whatever, can play with all the fields because you have access to all the fields. So you can change everything basically because everything is open, all the headers are open. So you can look into the headers, not only changing the ports, but you can also change acknowledgements, for example. There are middle boxes, sometimes called proxies, that can acknowledge packets on behalf of another computer. So acting as a server somewhere in between, acknowledging parts. So you can do many things in between, but this breaks the end-to-end paradigm and causes some problems. So basically, there's no header field that a middle box cannot change. Is this a problem? Well, it depends. So most middle boxes, and that's one of the big problems, they make certain assumptions of the format of the protocol headers. So to change the header is almost impossible, and this means we go for TCP or for UDP. And if you want to introduce your fancy fast protocol, it doesn't work. Because the middle boxes think, what's this? I rather drop the packet. I don't know. I cannot handle this, so I drop it. Although it's a valid IP packet, but it's a different protocol inside, so layer 4 protocol. So changes of the header, very difficult. Additionally, the middle boxes try to modify some fields. So if you have a different header, okay, so what happens? Or even if you have a TCP header, maybe on purpose you set a certain value somewhere, but maybe the middle box changes this. And then also many middle boxes, they simply restrict utilization of certain extensions. So I touched this already when I talked about options. So quite often, many options are not supported. And it can be shown that the network does not forward packet with certain fully official options set. So although you follow the standard, the network will not forward your traffic. This is strange, but that's the way it is. So in the end, we can say the use of TCP or UDP as transport layer is more or less hardwired, and that is the ossification. So important for you is to understand what this ossification means, where the ossification comes from, what are the reasons for this. Why do we have middle boxes? Try to find out different types of middle boxes. What is the purpose? Why do we have them at all? Aren't they only a problem? Well, there are reasons for having this, like firewalls, load balancers, like NAT boxes, etc. And in the end, you can think of what really happened then to our end-to-end principle. That's basically in the genes of our transport layer protocols. That's the idea. That's at the heart of the transport layer protocols, that they are end-to-end, but in reality, they are not anymore.